Right, so welcome to tonight's lecture. So my name is Harmtedy. We're going to be discussing sets. And to start with, we'll start with the definition of what a set is, and then we'll look at the set operations, and then we'll look at set algebra. Then from there, we'll go and look at the rules of De Morgan's rules, in short, about sets. Then after doing that, we'll always be having a mini test at least to help us know where we're moving, the pace at which we're moving, and to also help us understand or to know whether we're understanding what we're learning or not. All right, so let's quickly begin. So we'll start with the definition of a set. We have to understand what a set is even before we begin to do our thing. So a set, okay, so these are some of the subtopics that we're going to look at. So these are some of the subtopics. We define what a set is, define what a null set is, and everything. Okay, so a set is just a well-defined collection of distinct objects. Yeah, so it's just a collection of objects, in short. Of course, those objects should be defined. That's why in certain books, you discover that sets, not really in certain books, in most of the books, you discover that sets are denoted using a lot of different notations. You have set builder notations, you have interval notations, you have a lot of ways in which you can denote sets, in which you can list, rather you can write sets. Yeah, so these are some of the examples of sets. Yeah, so you can say this. You can see this one is in roster notation. This one is an interval notation. Even this one is also an interval notation. These are open brackets and intervals. These are closed brackets and intervals. So we're going to discuss these one by one as we proceed. So the other thing that we need to understand is a null set. What is a null set? So a null set is simply just a set that has no elements. It's a set, in other words, it's an empty set. That is a null set. So a null set is sometimes represented in roster form as this one, then in just other, and then another format in which you can present a null set is this one. Then the other type of set that we're going to look at is a singleton set. So a singleton set is simply just a set that only contains one element. So a singleton set is a set that only consists of one element. So an example of a singleton, so this singleton, an example of a singleton set is this one. And then this singleton set, sometimes it's known as a unit set. Yeah, so sometimes it's known as a unit set. So the reason why I've allowed today's lesson to be free is simple. It's because I want everyone, those that are doubting, those that are thinking maybe learning online will be a problem. So I want them to see for themselves. I want them to see for themselves, to see it's actually very easy for them to learn with me online. All right, so let's also now look at presentation of sets. So how do you present sets? How can you present sets? Remember, sets can be presented in 3 different formats. There are actually more than 3, but in this course, we're going to discuss only 3. There's a descriptive part or descriptive representation of set. And then we also have the set builder notation. Then apart from the set builder notation, you also have the roster notation. So the roster notation is the one that always carries these kinds of brackets. Then set builder notation, it also has these brackets, but it's a format which, for instance, you can give an example of. Okay, there's a question. So I'm asking, I can't hear anything. All right, so if you can't hear anything, I don't know how to reply to him because he can't hear anything. I think maybe that's his first time to use Zoom. Mostly if it's your first time, you tend to have challenges. Yeah, you tend to have challenges. Okay. Okay, someone to just kindly reply to this person in the messages. Or let me just reply to them. Okay. So if you can't hear anything, in most cases, it means that you just need to, there's a button that you need to press on the screen of your phone, or if you're using a laptop, on your laptop, when you just open Zoom for the first time. Yes. Thank you very much for replying to him. I don't know if it's her or him. Okay. All right, so this is what I'm just talking about. There's a description form where you just describe a set in using any language. It can be English, Chinese, I don't know, depending with the language that you are using in that mathematics course. Then there's also this part, which is the set builder form, which I also talked about. To look at it in details. Then there's also a roster form, which is just this one here, which is mostly used in our daily mathematics. All right. So let us quickly move on. So we also have to look at what a finite set and an infinite set. So today we're just looking at the basics, and I'm going to be a little bit fast because I don't know when you started, when you did sets, because I've seen you've gone as far as the radicals. I mean the surds. You've gone as far as the surds. So I need to move fast so that I should find those. But in case you have any questions, feel free to unmute yourself and ask a question. Yeah, that's why I'm here for you. That's why I'm here to help. So a finite set is simply just a set that contains a countable number of elements. So if you are able to count the number of elements in a set, then that particular set is a finite set. And then an infinite set is a set that contains an uncountable number of elements. So we consider all interval sets, all sets that have that can be represented in an interval form to be infinite. For instance, if you have 2,5, so 2,5, looking at the brackets that we're using here, this is an infinite set. It's an infinite set. So you can't manage to count the number of elements in this set. But if we say 2,5, and then we use these kinds of brackets, we represent it using the roster form. This means that there are only 2 elements in this set. So this implies that this is a finite set. You are able to count the number of elements. Okay. All right, so this is what I was just talking about. So a universal set is also just a set that contains it's actually a collection of all the sets in analysis. If you've been given, let's say for instance, set A, set B, and set C, if you add all those 3 sets, you put them together, you form what is called a universal set. So a universal set is a set which contains all elements or objects of other sets, including its own elements. Yeah, so that's what I was just talking about. Then we also have the power set. So a power set contains elements, rather it's just a set that contains all the subsets of any given set. So if you've been told to list a power set of any particular set, it means that they are telling you to list the subsets of that particular set. So for instance, you have set A is equal to, if you have set A is equal to A comma B, if this is your set A, and then they ask you to find the power set of A. So the power set of A is simply just going to be a set that contains the subsets of this set. So the first subset that is common in all sets is an empty set. Then followed by the set itself, there we have set A, the set which contains A. We also have the set that contains B. We also have the set itself, A, B. So that is a power set of A. So the set that contains the subsets of a particular set or a given set is called the power set. So if they say find n power set of A. If they ask you to find this, they are simply asking you to find the cardinality of the power set of A, which is just the number of elements of, in one sense, the number of elements or the number of subsets of a given set, which is just given by 2 to the power n. So if, for instance, you have 2 elements there, you just put 2 where there's n there, say 2 to the power 2, and then the answer will give you 4. So when you count the number of subsets here, you discover that there are 4. We have 1, 2, 3, 4. So that's what it means when they say cardinality of the power set of A. So cardinality is simply just the number of elements. All right, so that is a power set. And then when we talk about equality of sets, a set is said to be equal to another set if it contains the same number of elements and it also contains. So the first condition for one set to be equal to the other, number one, the number of elements should be the same. And then number two, it should contain exactly, let me not say the number, exactly the same element, exactly the same elements as the other set. So if A is equal to B, it means that A has exactly the same elements that are in B, and A contains the same number of elements that are in B. But if we say A is equivalent to B, the equivalence part means that the number of elements in A is equal to, the number of elements in A is equal to the number of elements in B. So if the number of elements in A is equal to the number of elements in B, it implies that the set A is equivalent to set B. So for this, you can have maybe 1, 2, 3, 4 as the elements in set A, and then set B maybe contains A, B, C, D, as long as the number is just the same. So if set B and set A have the same number of elements, we say these two sets are equivalent, but they are not equal. They are not equal in the sense that the elements are different. So for them to be equal, it means that the elements should also be equal, should also be the same. That's what it means when we talk about equal and equivalent sets. So equivalent sets only contains equal number of elements, but equal sets both sets should contain the equal number of elements, and the elements the elements should be the same, in short. Okay. So I've talked about this. And what I do is that I will not only send the link to the video, but I'll also make sure that I send the slides so that you can have time to go through it on your own. Then this discrete and continuous, this is just the same as what we talked about. Yeah. So when you say this set is a discrete set, it means that the set can be listed, meaning it contains a countable number of elements. When you say it is continuous, meaning it does not contain a countable number of elements. The elements that are there are uncountable. Yeah, so a continuous set can either be represented in this format or in this format. So when we talk about continuous sets, we're simply discussing the interval notation. So all those sets that are in interval notation, they are continuous sets. Okay, let's look at the set builder notation. Yeah, so when you talk about the set builder notation, the roster notation is this one, interval notation is this one, and then set builder notation now is the one that we're going to talk about. So how can you represent this set in set builder notation? It's something that is straightforward. So look at the rules of sets at, we look at the rules of sets, the De Morgan's rules. I know maybe those are the sets that you are expecting me to teach today. So look at them later, don't worry. and then we'll look at even other things. But the most important thing is the foundation. So once you just understand, you recall, you are able to remember all these simple things. It will not be easy for me to come and explain the other complicated set subtopics that we are yet to discuss. But if I skipped all these and just went straight to those things, you would have maybe been getting confused. So when you talk about set builder notation, so this one can be written as so this one can be written in set builder notation. We can just write this as so we can just write this as this is set A. Let me just write it here. So set A is equal to, we open the brackets, and then we're going to say X is such that, so you can either use two dots like that, or you can just draw a line like that. X is such that X is a member of, so this X is a member of natural numbers. You can either say natural numbers or whole numbers. But the most important thing in this case, since we have numbers that have been skipped from 3 to 8, there are numbers that have been skipped in between there. So we can just say X is equal to, just write that 1, 2, 3, then 8. So this one is straightforward because there are numbers that have been skipped. If these numbers were continuous up to 8, it would have been easier for us to just say X is a member. X is such that X is a member of natural numbers from 1 to 2. From 1 to 8, or between 0 and 8. That would have been a nice way of doing of listing this. So if this was continuous, if for instance it was like this, if it was discrete, but in between here, if it was continuous, the numbers were continuing up to 8. If we had 1, 2, 3, 4, 5, 6, 7, 8. If this was the case, would have said A is equal to X such that X is a member of natural numbers, and then where we say 1 is less or equal to X less or equal to 8, would have done this. So this would have been the answer. So what this part means is that if we are writing numbers or listing numbers from 1 to 8, and these numbers are supposed to be natural numbers. This one is also straightforward. So this one, what you just have to do is, you can also write it in simpler form as B is equal to X is such that X, or let me just write it like this. Just say X is such that, and then we say, these numbers are ranging from where? We say X is a member of real numbers. So X is a member of real numbers where X, or let me not say where X, but let me just say, we have 0. These are numbers ranging from 0, then up to 2. So I'm not writing less or equal to because of this kind of brackets that have been used here. So I'm going to explain what these brackets mean as we begin to do interval notations, or let me just briefly talk about them. So if you have brackets like this, you have 1, 3. So when you write this, it means that 1 and 3 are not part of this set. They are not part of this set. But if I write like this, 1, 3, it means that 1 and 3 are part of the set. So these are called open brackets. These are called closed brackets. And then if I have something like this, 1, 3, it means that 1 is not part of the set. We're just talking about numbers between 1 and 3. And then 3 is also part of the set. All these three sets that I've written here are infinite set. So same applies if I write like this, 1, 3. So this implies that 1 is part of the set, but 3 is not part of the set. So whenever you see this kind of a bracket here, it means that that number where the bracket is not part of the set. So this can also, so this one can be written as 1 less or equal to x less 3. So while there's just this less without adding an equal symbol there, it means that we are using this kind of a bracket, meaning 3 is not part of the set. But if it's part of the set, there's always supposed to be this equal symbol down there. So this is what this meant. So this meant that we're talking about numbers between 0 and 2, and we are not going to add 0 and 2 in that set. So when we talk about set C can also be written in the same way as x, such that x is a member of real numbers. And then these real numbers are ranging from 0 to, okay, let me not do this. Let me just use inequalities. Okay, I know I can't erase. Anyway, let me write just like this. So we have 0. So forget about this. Okay, so we have this one here, 0 to 2. So I'm going to say 0. And of course, when you look at the bracket which is at 0, it shows that 0 is part of the set. So I'm going to say less or equal to x, which is less than 2. This is it. Then when you talk about D is also going to be written in the same way, which is x is a member of real numbers. So real numbers, this is just a set of, when you get rational numbers, you add them to irrational numbers. When you combine the set of rational and irrational numbers, you come up with a set that is called the set of real numbers. So this side we're going to have, we know 0 is not part of the set, but 2 is part of the set. Okay, let me just write it again. So we have x is such that x is a member of real numbers, where 0 is less than, 0 is not part of the set, so 0 is less than x, which is less or equal to 2. So this is D. All right, so these are the solutions. All right, so subsets. So a subset is simply just a set that is a set. Okay, let's define this set in terms of A and B. So a set A is a subset of another set B if all the elements in set A are elements of set B. So this is an example that you can see here. So if the elements of set A are elements of set B, we consider A to be a subset of set B. So this one is straightforward. Yeah, and then these are some of the examples. Okay. So the Venn diagram, we all know what a Venn diagram is. So I'm trying to rush because some of these things are simple. And next time when we meet, I'm sure that's when we're going to learn detailed things in what's this in your course, which is mathematics. So for now, I'm looking at the foundation of mathematics. These are simple and straightforward. So when you look at the Venn diagram, these are objects that are only contained in A. Then this is an intersection set. Then this one, this part contains objects that are only in B. So we'll look at the laws of the sets, like De Morgan's laws, the complement laws, and you will look at the supplementary laws, the what's this, distributive laws. We'll look at all those sets. Let's first look at the foundation. It's very important to look at the basics first. So the union set, when we talk about union set is just a set that is formed by combining two sets. And then an intersection set is just a set that is formed by getting common elements between two given sets, and then you write them together. The answer that you get is called an intersection set. So this is an example of an intersection set. This is an example of a union set. So complement. So when we talk about complements, if you have maybe, let's say, a set A, then you have maybe set A, this is set A, then you have 1, 2, 3, 4. Then you have the universal set there. Then they ask you to list a complement. So a complement is simply just listing the elements that are not in A, but they are present in the universal set. So these elements are simply just 3 and 4. So elements that are outside A, but they are supposed to be in the universal set. That are that's what we call the complement. That's how you can define. That's the simplest way of defining a complement set. Okay. So if you have questions anywhere, feel free to ask. Okay. So set difference. So when you talk about the set difference, when you see A minus B, this one is just the same as A intersection B complement. So wherever you see A minus B, this is just a set difference. This is just the same as A intersection B complement. If you, for instance, find X minus Y, this one is just the same as X intersection Y complement, which is very, very much simple and straightforward. So this is the simplest way you can solve the set differences. So in other words, you're finding the intersection set between what is in A and what is not in B, but part of the universal set. So in other words, you are listing elements in A, excluding those elements that are in B. That's what it means. In other words, when you say A minus B, this one is just the same as A intersection B complement, meaning you are listing the elements that are in A, but they are not in B. Elements that are in A, but they are not in B. That's what it means. So if you have any questions, feel free to ask. So this is what I was discussing. You list the elements that are in A, but they are not in B. Okay. Symmetric difference of two sets. This is quite, I've not seen it in your tutorial sheet, so I don't think it can be of use to you. But it's also important whenever you see A, then there's a triangle, that's a symmetric difference of two sets. That's a symbol, triangle. This one is just the same as, writing A union B, and then minus A intersection B. So this is what it means. The symmetric difference of two sets A, then you have a triangle in between B there. So this is just the same as A union B minus A intersection B. As simple as that. Let us look at some of De Morgan's laws in this remaining last 10 minutes. These laws, we have these laws. So when you have this one here, when you use the associative law, or rather the distributive law to distribute this, you're going to have this. This one is supposed to be, there was a mistake here. This one is supposed to be union, not intersection. And then this one is supposed to be intersection, not union. There was a mistake. Yeah, so A minus B, if you have A minus B union C, if you use distributive law, you're going to distribute this A minus to everything in the brackets. So A minus B, I'll start with A minus B. I'll write it there. And then the symbol which is between there is union. So I'm going to write union there. Then open brackets, A minus C. That is how you distribute. The same applies to this part. You also distribute in a similar way. A minus B, then intersection A minus C. This is what you have this side. Then the other part, the other most important part is this one. If you have B union C, then complement. Whenever you distribute this complement to everything in the brackets, you have to make sure that the sign in between changes. If it's union, it should become intersection. So if we distribute this complement, we write it on B. So the sign there will change to become intersection. Then you have C complement there. That's what that means. Same applies to this part. You do the same. If you have a B complement intersection C complement, if you factorize the complements, you still If you factorize the complement, you write it outside like this. You just have to write the same letters that you have, B and C, but of course the sign here has to change. So I've just written this in the opposite. Okay, so if you feel you have a question, you feel free to unmute yourself and ask. So these are some of the other set laws that you need to understand. These are some of the other important set laws that you need to know. So if you have a union complement is equal to the complement of a universal set, not union rather, the complement of the universal set. Sometimes it can be written as E complement. The answer is simply just an empty set. And then the complement of an empty set is simply just the universal set, which can also be written as U. And then A intersection A, if for instance you have set A, you have set A there, then this is a universal set. You have set A. So if they say A intersection A, you've been told to shade the common elements between A and the same A again. It's simply just the same as shading A. So A intersection A is also just equal to A. A intersection A complement, the same set, I'm going to use the same set. You have A, and then intersection A complement. In other words, you are trying to find the common element between what is in A and A complement. We're trying to find this one, A intersection A complement. So you're trying to find the common elements between A and what is outside A. And when you look at this diagram, you can agree with me to say there is no common element between what is inside this A and outside A. Hence, this one gives you an empty set. Then when you say A union A, when you combine two sets, A and A, the answer that you get will simply just be A. Because remember, when you're listing the elements in what's this, when you're listing elements, when finding the union set, you always have to make sure that you list each repeating element once, not more than once. So this will just give you A. Then when you say A intersection universal set, so when you find the intersection set between the universal set, between everything in the universal set and A, the answer will still be A. Then A union universal set, when you combine the set A with what is in the universal set, the answer will still be the universal set. So when you combine what is in A and what is in the universal set, the answer will be the universal set. And then when you find A complement, intersection A complement, the answer will still be A complement. That's how it is. Because you're trying to find what is outside A, you find the common elements between what is outside A and also what is outside A. The answer will be exactly what is outside A. So A intersection, we move on to the last part, which is A union, A union A complement. So A union A complement is simply just like this. So A union A complement, you're simply listing what is inside A, you combine it with what is outside A. So when you combine what is outside A and what is inside A, the answer that you get is simply just a universal set. Yeah, so these are some of the basic important laws that you need to know and understand about sets. All right, so let's quickly move on and see these other laws on sets in the last 3 minutes that we have. So we have what is called the commutative law. So the commutative law only deals with the arrangement of letters in the operation. So when we say A intersection B, if A intersection B is equal to B intersection A, it means that the operation intersection, it obeys the commutative law. So this is also going to be discussed when we start dealing with the binary operations. So immediately after doing sets, we're going to binary operations. Not today, of course, but probably in the next what's this discussion that we're going to have. We're going to be discussing binary operations. So the way it is that if you change the arrangement of letters and the answer that you get is still the same, then that given operation obeys the commutative law. So commutative law just deals with the arrangement of letters. And then associative law is it just deals with the arrangement of brackets, in short. If the brackets were on B and C, in this case, they'll be on A and B. So if you get the same answer this side, on the left-hand side and on the right-hand side, it means that the given operation obeys the associative law. And then distributive law, you just distribute it in the similar way I distributed that A minus B intersection C on the other slide that we are looking at. So the same way I distributed that is what you do. So we are going to do this. You say A intersection B, you write it there, and then you get the same A intersection C, you write it on the other side, and then the union set there is the one that you put in between there. Then we have the De Morgan's laws, which I've already talked about. It's just a matter of changing the complement. When you distribute the complement in the brackets, you change the sign in between there. So this is what it means. So if you have any questions, we're just remaining with 1 minute. The link will will cut anytime soon. If you have any questions, feel free to ask before the link cuts. Feel free to ask. Otherwise, this is the end of the first lecture that we've had. Tomorrow, we're going to have physics. So those that are willing to pay, you can inbox me. I send you the line. Once you pay, I'll add you to the new group where I'll be posting all the links for learning. All right. So
thank you, sir. Thank you so much.
All right. You're most welcome. Thank you very much. See you in the next lesson that we are going to have. My name is Harmtedy.